Alright, today's lesson's on Chapter 2, Section 3. We are learning polynomial synthetic division. Synthetic division is a shorter, generally faster way of dividing polynomials by their factors. There are some limitations to when we can use synthetic division, but for the most part, if you're looking for rational factors to polynomials, it's the fastest and most efficient way of doing it. So many of you have probably already done this before. I'm going to go through the process again very quickly with you. Just a little bit of vocabulary here. When you do synthetic division, the quotient that you get or the answer you get is called the depressed polynomial. And that's what remains after you take out the factor. So it's pretty much doing the factoring for you. Because remember, when we factor, we take out one of the multiples and then we see what's left over. The first examples are going to give you the factor to use. Eventually we're going to be having to come up with our own numbers to try and synthetically divide. And the most difficult part is that people forget, what number do I synthetically divide? Well, you have to actually take the root of the factor and do the synthetic division with that number. So in letter A here, 2x to the fourth minus 5x squared plus 5x minus 2, we're actually going to be dividing that by the root. Okay? So you first want to find the root that you're dividing out. Remember, the root is not the factor, so it's not x plus 2. The root is what makes this a 0. So that would be when x is equal to negative 2. And so that's what we're going to use for our synthetic division. In the notation, we usually block that off in a little L bracket there. And then the shortened version, we just take the coefficients of the polynomial that we're dividing it out of. So the only tricky part is that if you're missing any terms, you need to represent that with a 0 for its coefficient. So in other words, in this one we have 2x to the fourths, so that's going to be a 2. But then we have no x cubes. So for my next placeholder, I'm going to put 0. So again, just like we did long division, we had all of our columns lined up by our terms. It's the same thing here. We have 2x to the fourths, 0x to the thirds, negative 5x squareds, 5x's, and then negative 2 for our constant. Okay? And so the process is that the first number that you have automatically gets a free ride to the bottom. That's going to be in our depressed polynomial. Now, for every other column as we go, we're going to take the number in the depressed polynomial, multiply it to the root, and then put that in our column and then add that up. So we do 2 times negative 2 is negative 4. And we'll add that to the 0. Negative 4 times the negative 2 is 8. Add that to the negative 5 is 3. 3 times negative 2 is negative 6. That gives us negative 1. And then negative 1 times negative 2 is 2. 2 plus negative 2 is 0. And so if we get a 0 for the end, that means that the root, or the factor, was an actual factor of the polynomial. And then what remained here, down here, this is the depressed polynomial. Okay. These are the coefficients of the terms of our depressed polynomial. Now our depressed polynomial always starts 1 degree less than we had before. So we had x to the fourth. Now this is going to be 2x cubed minus 4x squared plus 3x minus 1. Okay. If we had a remainder, we could add that to it over the dividend, just like we were with the long division yesterday. But since they're not asking for anything other than for us to divide, we're done right there. Okay. So let's take a look at another example, one where you have kind of a unique root. The root for this one is, again, when 2x minus 3 would equal 0. So if I set that equal to 0 and solve for x, we get 3 halves. So the root would be where x is equal to 3 halves. And so I'm going to put that factor into a bracket and then take my coefficients out. So 10x cubes, negative 13x squareds, 5x's, and then negative 14 for my constant. Remember that the first term goes straight to the bottom because we don't have anything in our depressed polynomial to start with. So the first term goes right down. 10 times 3 halves, you can think of that as 10 times 3 divided by 2 is going to be 15. If we add these up, that's 2. 3 halves times 2 is 3, so this is 8. And then 8 times 3 halves would be, let's see, 12. And so we end up getting negative 2. So this is our remainder. That's not actually part of the terms for our depressed polynomial. These three terms, or these three coefficients, however, are part of the terms. So the answer would be 10x. Again, you reduce your power by 1. 10x squared plus 2x's plus 8 minus 2. And then we use what was our original expression that we were dividing by, 2x minus 3. Okay. So that's synthetic division. I want you to try these two on your own. Okay, if you check your answers, make sure that you pulled the right coefficients out, 4, 3, negative 1, and 8 for the first one, and that you picked the right root to divide into it. It was 3. Your remainder was 140, and so this is your answer. 3b, be careful with your root for this one. It should be negative 1/3, and your coefficients go across like so. You may notice in your textbook that a lot of times they like to factor out any GCFs, even though they don't say to in the problem. So they may have written their answer like this: 2x cubed plus 3x squared minus 6x minus 2 plus 3 over 3x plus 1. All they did was factor a 3 out of all of the terms. Okay. The next thing we're going to do is what's called the remainder theorem. The remainder theorem is very simple. If a polynomial is divided by x minus c, okay, the remainder that you get, the remainder is that last term that we get. So these numbers that I'm circling, that's always our remainder. The remainder that you get would be what would happen if you plugged in f of c. Okay, so that's a really easy way for us to solve a function or plug a number in if we don't have a calculator readily available. Okay. So for example, in this problem, they said that there's a function that describes the number of tickets sold at a football season. X is the number of games played. Use the remainder theorem to find the number of tickets sold during the 12th game of the football season. So we're trying to find out what t of 12 is equal to. And so what we want to do is we want to divide this polynomial by x minus 12. That's what the theorem states. So the root for that is going to be 12. And we just pull all of the coefficients out. So it's going to be 1, negative 12, 48, and 74. And so if we can get to the remainder at the end, that would tell me what t of 12 would be. So we carry down the 1. This is 12. That's 0. 0 times 12 is 0. This is 48. So we do 48 times 12. Let's see, 48 times 12. It's going to be 96, 48, 6, 17, 576. I'm going to do 576 plus 74. That's going to be 650. So that would be how many tickets they would sell at the end of the season. That's your answer. Okay, so on your own now, try and do the same thing, but for the 13th game of the season. So instead of using the binomial x minus 12, we'll use x minus 13, find your root from there, and then do the synthetic division. Okay, check your synthetic division. If you did it right, you should have gotten 867. Okay. Okay, the last thing we're going to be doing with synthetic division is using them to determine factors. It's pretty much the same thing you do with long division. If you get a remainder of 0, then you know that the binomial was a factor of the polynomial. If you don't get a remainder of 0, then it's not. So it's a fast way we can check for factors of the polynomial. So these problems are a little unique because they're going to give you 2. You have to determine which one of them is a factor, if either of them is. So we're just going to do 2 really quick synthetic divisions. Remember to take the roots of each of the factors. So the root of x minus 1 is 1. We're going to synthetically divide that into 4, 21, 25. Make sure all of your terms are covered. Don't forget to place any zeros if you need to, but we have all of ours here. So we carry down the 4. 4 times 1 is 4. 4 plus 21 is 25. 1 times 25 is 25. That's going to be 50. 50 times 1 is 50. This is 45. And at some point you can usually start to tell that it's not going to really work out for you. So this one, it does not get you 0, so 1 is not a factor. Let's try negative 3. 4, 21, 25, negative 5, and 3. So it's negative 12. It's going to be 9. It's negative 27. It's negative 2. So far, so good. 6. This is 1. And negative 3. So we got 0 for our remainder. Okay, this is the depressed polynomial down here, okay? It's just, these are the coefficients of what we're going to use. So it says, use the binomials that are factored to write a factored form of f of x. So our factored form would be, we take the x plus 3 that is a factor, and we take the depressed polynomial with all of its terms replugged in. So 4, again, it reduces from the original one by 1 degree. So this is going to be 4x cubed plus 9x squared minus 2x plus 1. Okay, try B on your own. Okay, so here's the answer to B. B, both of the factors actually were factors of the polynomial. So you should have gotten the remainder 0 regardless of which one you picked. I did want to show you, however, that if you wrote the first one with negative 4 in factored form, you got x plus 4 times 2x squared minus 9x minus 5. Okay, now if we factored that further, the 2x squared minus 9x minus 5 would factor to be 2x minus 1 times x plus 5. There's the x plus 5 that we, whoops, wait a second, did I do that wrong? This should be negative 5 here, and positive 1. There's the x minus 5 that we should have had from the beginning. So it doesn't matter the order that you pull out your factors, you'll end up getting them either way at the end, if indeed they are factors. And the same thing if you'd done the 5 first. You'd have gotten that it was 2x squared plus 9x plus 4, and when you factor that, you get 2x minus 1 and x plus 4. There's the x plus 4 that you started with over here. So either way, fully factored, this works out to be x plus 4 times 2x plus 1 times x minus 5. They didn't ask for the fully factored form, but that's eventually what we're going to work towards, is fully factoring polynomials. Okay, so that's it for today. The classwork will be, actually I'll put it right up now for you. This is assignment 30, 19 through 37 odd. Okay, have a great day.